Dear students, greetings for the day. In this class, we shall discuss the important, one of the important branch of physics, that is properties of matter. This branch consists of the different sub articles: elasticity, surface tension, and viscosity, and about fluid motion. So now in this chapter we shall discuss in detail about the elasticity topic. So all the bodies undergo change in size, shape, or both when they are subjected to the action of the external force. This is known as deformation. So all the bodies deforms under the action of force. A body whose size and shape do not change under the action of a force is known as perfect rigid body. This is only an ideal concept. In nature, there is no perfect rigid body. All the bodies can be deformed to some extent by applying suitable forces. But all the solids, liquids, gases resist the change in volume. Liquids and gases cannot offer any resistance to the forces tending to change their shape. But most of the solids offer resistance to the deforming forces. Now we shall know what is meant by deforming force. The force which changes or tries to change the size or shape of the body without moving it as a whole is called deforming force. Displacements are the absolute change in position of a point on the object. Deflection is the relative change in external displacements on an object. Strain is the relative internal change in shape of an infinitesimally small cube of material and can be expressed as a non-dimensional change in length or angle of distortion of the cube. Strains are related to the forces acting on the cube, which are known as stress by a stress-strain curve. The relationship between stress and strain is generally linear up to a certain extent and reversible up until the yield point, and the deformation is elastic. The linear relationship for a material is known as Young's modulus. Above the yield point, some degree of permanent distortion remains after unloading and is termed as plastic deformation. The determination of stress and strain throughout a solid object is given by the field of strength of materials and for a structure by structural analysis. Now we know about engineering stress and engineering strain. These are approximations to the internal state that may be determined from the external forces and deformations of an object, provided that there is no significant change in size. When there is a significant change in size, the true stress and true strain can be derived from the instantaneous size of the object. In the coming figure, it can be seen that a compressive loading indicated by the arrow has caused deformation in the cylinder so that the original shape dashed lines has changed, that is deformed into one with bulging sides. The sides bulge because the material, although strong enough to not crack or otherwise fail, is not strong enough to support the load without change. As a result, the material is forced out laterally. Internal forces In this case, at right angles to the deformation, resist the applied load. So, in this curve, we observe the with the stress how strain changes. So, up to yield strength, the curve is linear, that is, stress is proportional to strain, and after that, it's slowly increasing, and at maximum point it has ultimate strength, and even if we increase the stress, then break point occurs. So Young modulus is obtained by rise by sun, that is slope. By obtaining the slope of the curve, it gives the Young's modulus. Now we shall know what is meant by restoring force. The force which develops inside the body against a deforming force and tries to bring the body back to its original size and shape is called restoring force. So, the force which is developed inside the body against a deforming force and tries to bring the body back to its original size and shape is known as restoring force. In physics, the restoring force is a force which acts to bring a body to its equilibrium position. The restoring force is a function only of position of the mass or particle, and it is always directed back toward the equilibrium position of the system. The restoring force is often referred to in simple harmonic motion. The force which is responsible to restore original size and shape is called restoring force. As an example is the action of a spring. An idealized spring exerts a force that is proportional to the amount of deformation of the spring from its equilibrium length exerted in a direction to oppose the deformation. Pulling the spring to a greater length causes it to exert a force that brings the spring back towards its equilibrium length. The amount of force can be determined by multiplying the spring constant of the spring by the amount of stretch, is also known as Hooke's law. Another example is of a pendulum. When the pendulum is not swinging, all the forces acting on the pendulum are in equilibrium. The force due to gravity and the mass of the object at the end of the pendulum is equal to the tension in the string holding the object up. Tension in the string T is equal to mg, which is equal to weight of the simple pendulum bob. When a pendulum is put in motion, the place of equilibrium is at the bottom of the swing, the place where the pendulum rests. When the pendulum is at the top of its swing, the force bringing the pendulum back down to this midpoint is gravity. As a result of gravity can be seen as the restoring force in this point. Let us know the definition of elasticity. Whenever a force acts on a body, it undergoes some deformation and the molecules offer some resistance to the deformation. When the external force is removed, the force of resistance is also vanishes and the body springs back to its original state. This is possible only when the deformation is within certain limit, which is known as elastic limit. Consider a piece of rubber. Suppose that two equal forces are applied at its ends in opposite directions, then the piece of rubber stretches. Here, the piece of rubber is deformed and so the applied forces are called deforming forces. As soon as the deforming forces start acting on the body, the restoring forces develops inside the body in opposite directions to the deforming forces. When the deforming forces are removed, these restoring forces brings the piece of rubber back to its original size and shape. Elasticity is an economic measure of how sensitive an economic factor is to another. For example, changes in price to supply or demand, or changes in demand to changes in income. If a demand for a good or service is relatively static, even when the price changes, demand is said to be inelastic, and its coefficient of elasticity is less than 1. Examples of elastic goods includes clothing or electronics, while inelastic goods are items like food and prescription drugs. Now we shall know the definition of elasticity. The property of certain materials of returning back to their original size and shape after they remove the deforming force is called elasticity. Elasticity is the general property of a matter. So, elasticity is defined as the property of the material by which it regains its original size and shape when the deforming forces acting on the body are removed. Generally, the molecules in solids occupy definite positions. When the deforming forces are applied on the body, the distance between two molecules change. On stretching, intermolecular distance increase, and on compression, they decrease. In both cases, molecules are displaced from their normal situation. In both the cases, the molecules are displaced from their normal positions, and restoring forces comes into play to bring the molecules back to their original positions. The elastic limit depends marked only on the type of solid considered. For example, a steel bar or wire can be extended elastically only about 1% of its original length, while for strips of certain rubber-like materials, elastic extensions, elastic extensions of up to 1000% can be achieved. The restoring forces are due to the cohesive forces of attraction among the molecules of the body. As long as the deforming forces are small, the restoring forces are equal and opposite to them. Within the elastic limit of the body, the restoring forces will be proportional to the deforming forces. When the deforming forces are removed, the restoring forces brings back the molecules to their normal positions, and the body regain its original size and shape. So these restoring forces are due to the cohesive forces of attraction between the molecules of the body. So when the deforming forces are removed, then restoring forces bring the molecules in the body to the normal position so that the body regain its original size and shape. Steel is much stronger than rubber, however, because the tensile force required to effect the maximum elastic extension in rubber is less by a factor of about 0.01 than that required for steel. The elastic properties of many solids in tension lie between these two extremes. The different macroscopic elastic properties of steel and rubber result from their very different microscopic properties. The elasticity of steel and other metals arises from short-range intra-atomic forces that when the material is unstressed. In a simple tension test, the elastic response of a material is such as steel and bone is typified by a linear relationship between the tensile stress, that is tension or stretching force per unit area of cross section of the material, sigma, and the extension ratio, that is difference between the extended and initial length divided by the initial length, E. In other words, sigma is proportional to E. This is expressed as sigma equal to capital E into small e, where capital E is the proportionality constant called Young's modulus. So when stress is proportional to strain, then stress by strain is equal to constant. So linear stress by linear strain gives the elastic constant, that is Young's modulus. The value of elasticity moduli depends on the material. The ratio of its values for steel and rubber is about 1 lakh. The equation sigma equal to capital E into E is known as Hooke's law, and it is an example of a constitutive law. It expresses in terms of macroscopic quantities something about the nature or constitution of the material. Hooke's law applies essentially to one-dimensional deformations, but it can be extended to more general three-dimensional deformations by the introduction of linearly related stresses and strains, generalizations of sigma and E that account for shearing, twisting, and volume changes. The resulting is generalized as Hooke's law, upon which the linear theory of elasticity is based, provides a good description of the elastic properties of all materials, provided that the deformations correspond to the extensions not exceeding about 5%. This theory is commonly applied in the analysis of engineering structures and of seismic disturbances. The elastic limit is in principle different from proportional limit, which marks the end of the kind of elastic behavior that can be described by Hooke's law, namely that in which the stress is proportional to the strain, or equivalently that in which the load is proportional to the displacement. Now we shall know what is meant by elastic body. Nobody is perfectly elastic in nature. So the materials which regain their original size and shape after the removal of external force is known as elastic body. In perfect quartz fiber is nearer to the perfect elastic in nature. Rubber is less elastic than steel. Solid substances like rubber, metal, and crystals are an example of elastic bodies. So a body which regains its original size and shape completely after the removal of deforming force is called as elastic body. Example is also elastic spring. A spring is an example of an elastic body that can be deformed by stretching. For example, if we take spring and it is connected to some support, and when we put some weight at the other end of the spring, then it stretched, its length increases by x. So a restoring force F bar acts in the direction opposite to the displacement of the oscillating body, that is towards the upward direction, so that when we remove the weight, again it due to which restoring force, the spring again contracts and it comes to original length by contracting in the upward direction. Therefore, F is proportional to minus x or F equal to minus k into x. It denotes that restoring force always acts in the direction opposite to the displacement of the oscillating body. Now we shall know what is meant by plasticity. Plasticity is also the nature of the bodies, and when they are subjected to the external force, they undergo deformation, but when the deformation forces are removed, they do not regain their original size and shape. So this property of not regaining the original size and shape when the deformation forces are removed is known as plasticity. So if the deformation is beyond the elastic limit, the body loses its property of elasticity to some extent. At this stage, if the deforming forces is removed completely, the body will not return back to its original size and shape, and the deformation will remain in it permanently. The bodies like wax, flour, duff, soldering lead, chewing gum, mud, etc., which exhibit the above nature are called plastic or inelastic bodies, and this property is called plasticity. In engineering, the transition from elastic behavior to plastic behavior is known as yielding. The plastic deformation is observed in most materials, particularly in metals, soils, rocks, concrete, foam. However, the physical mechanisms that cause plastic deformation can vary widely. At a crystalline scale, the plasticity in metals is usually a consequence of dislocations. Such defects are relatively rare in most crystalline materials, but are numerous in some and part of their crystal nature. In such cases, plastic crystallinity can result. In brittle materials such as rock, concrete, and bone, plasticity is caused predominantly by slip at microcrack. In cellular materials such as liquid forms or biological tissues, plasticity is mainly a consequence of bubble or cell rearrangements, notably T1 process. For many ductile metals, tensile loading applied to a sample will cause its behavior in an elastic manner. Each increment of load is accompanied by a proportional increment in extension. When the load is removed, the piece returns to its original size. However, once the load exceeds a threshold, the yield strength, the extension increases more rapidly than in the elastic region. And now when the load is removed, some degree of extension will remain. Perfect plasticity is a property of materials to undergo irreversible deformation without any increase in stresses or loads. Plastic materials that have been hardened by prior deformation, such as cold forming, may need increasingly higher stresses to deform further. Generally, plastic deformation is also dependent on the deformation speed, that is higher stresses usually have to be applied to increase the rate of deformation. Such materials are said to deform viscoplastically. The inability of certain materials to regain their original size and shape after removing the deforming force is called plasticity. So, in this figure, some external force is applied on the cylinder, then its length increases. So here, the ratio of applied force per unit area of cross section of the cylinder is known as stress. In this figure is shown as sigma is equal to F by A on y-axis. So with the increase of stress, strain also increases, that is the change in shape of the body, that is length increases. And the slope of the curve gives the moduli of elasticity, that is nearly M modulus, which is nearly equal to in this case 0.2%. Stress strain curve in this figure showing the typical yield behavior for non-ferrous alloys. Stress sigma is shown as a function of strain to elastic limit and proportionality limit, elastic limit, and offset yield strength is shown in this figure. Elastic or plastic body or inelastic body. A body which cannot regain its original size and shape after the removal of deforming force is known as plastic or inelastic body. Now we shall know about the definitions of stress and strain and types of stresses and types of strain. When the deforming force is applied to an object, the object deforms. In order to bring the object back to the original shape and size, there will be an opposing force generated inside the object. The restoring force will be equal in magnitude and opposite in direction to the applied deforming force. The measure of this restoring force generated per unit area of the material is called stress. So stress is defined as the restoring force per unit area of the material. It is a tensor quantity denoted by Greek letter sigma, measured using in Newton per meter square or in Pascal in SI system. So mathematically expressed as stress sigma equal to F by A, where F is the restoring force measured in Newton, A is the area of cross section measured in meter square, and sigma is the stress measured in Newton per meter square or in pascals. So the restoring force developed inside the body per unit area of cross section of the material when the deforming force is applied is known as stress. Stress units. Stress can be expressed using multiple units. So fundamental units in SI system kg per meter per second square, in SI unit Newton per meter square, and it is also called Pascal in SI system. So it is measured in terms of Pascal. And SPS unit is foot pound per foot square. Or in inches, PSI, that is 1 pound foot per inch square. Types of stresses. There are several types of stress in physics, but mainly it is categorized into two forms, that are normal stress and a tangential stress and steering stress. So here now we shall discuss some stress types, that is normal stress, longitudinal stress, tensile stress, comprehensive stress. So longitudinal stress is observed in the case of the wire, in which the length increases with the applying of external force on the wire. And also there is bulk stress or volume stress, which changes the volume of the body when external force is applied. Another one, shearing stress or tangential stress. So when we apply external force on the face of a square or rectangular block, then its upper surface shifts by an angle. So it becomes parallelogram shape. So the angle of shifting is measured in terms of stress. Now we shall discuss in detail about normal stress. As the name suggests, the force stress is said to be normal stress when the direction of the deforming force is perpendicular to the cross-sectional area of the body. The length of the wire or the volume of the body changes, stress will be at normal. Normal stress can be further classified into two types based on the dimension of force: longitudinal stress, bulk stress, or volume stress. So when we apply external force on the wire, its length increases. It is known as longitudinal stress. When applied external force changes the volume of the body, then it is known as bulk stress or volumetric stress. For example, to understand the longitudinal stress, we consider a cylinder. When two cross-sectional areas of the cylinder are subjected to equal and opposite forces, the stress experienced by the cylinder is called longitudinal stress. Then its length or height increases. So longitudinal stress equal to deforming force by area of cross-section. So it is equal to force per unit area, or F by A. As the name suggests, when the body is under longitudinal stress, it is equal to F by A. The deforming force will be acting along the length of the body. Longitudinal stress results in the change in the length of the body, hence thereby it affects slight change in diameter. The longitudinal stress either stretch the object or compress the object along its length. Thus, it can be further classified into two types based on the direction of deforming force: tensile stress and as compressive stress. Let us know about tensile stress. If the deforming force or applied force results in the increase of the object's length, then the resulting stress is termed as tensile stress. For example, when a rod or wire is stretched by pulling it with equal and opposite forces outwards at both ends. Compressive stress. If the deforming force or applied force results in the decrease in the object's length, then resulting the stress is termed as compressive stress. For example, when a rod or wire is compressed, squeezed by pushing it with equal and opposite forces inwards at the both ends. Bulk stress or volume stress. When the deforming force or applied force acts from all dimensions, resulting in the change of volume of the object, then such stress is called volumetric stress or bulk stress. In short, when the volume of the body changes due to the deforming force, it is termed as volume stress. Next, steering stress or tangential stress. When the direction of the deforming force or external force is parallel to the cross-sectional area, then the stress experienced by the object is called shearing stress or tangential stress. This results in the change in shape of the body from rectangular to parallelogram shape. So here in this diagram, we shall know the different types of stress. Stress is divided into two types: normal stress, shearing stress, or tangential stress. Normal stress is again divided into longitudinal stress, volume stress or bulk stress. Longitudinal stress again divided into two types: tensile stress and compressive stress. Now we shall know what is meant by strain. When a force acts on a body, it undergoes some change in its shape known as deformation. This means the dimensions or shape of the body changes. The change in dimensions for unity dimension is known as strain. Therefore, strain is defined as the change in dimension for unit dimension of the body is known as strain. Objects deform when they are subjected to external forces. These deformations may be large or small, depending on the nature of the material and the stresses involved. Strain is the quantification of the deformation of a material. Linear strain occurs as a result of a change in the object's length. Linear strain is produced by compressive or tensile stresses. Shear strain occurs as a result of change in the orientation of the object's molecules. When the loading of an object causes tensile or compressive stress within the object, some change in length accompanies the stress. This deformation can be measured in absolute terms that describe the change in length of the object as a result of the loading. For example, the rubber band stretched 10 centimeters or the interval disc compressed 2 mm. The deformation may also be described in relative terms as the proportion of change in length, the difference between the underarmed and undeformed and the deformed length divided by the original length. This relative deformation measured is called linear strain. So linear strain is equal to the change in length by original length. Or if we consider area, strain is equal to change in area by original area. So here strain E is equal to L minus L0 by L0, where E is linear strain, L is stretched length, L0 is original undeformed length, and L minus L0 is change in length. The stress, which is equal to the deforming force per unit area, produces a strain, that is unit deformation in the body. Now we shall know what is meant by elastic limit. The maximum value of stress within which the body completely regains its original condition after the removal of the deforming force is called elastic limit. Now we shall know the dimensional formula and the units of stress and strain. So SI unit of stress is Pascal or Newton per meter square. Dimensional formula for stress is ml to the power minus 1 t to the power minus 2, which is obtained by dividing the force with the area units. So dimensional formula for stress is ml to the power minus 1 t to the power minus 2. And strain has no dimensional formula because strain is being a ratio of same physical quantities. So it has no units and dimensional formula because change in length by original length. So length unit is centimeter or meter divided by again centimeter and meter. So it has no units and dimensions. Now we shall know what is Hooke's law. Hooke's law states that within the elastic limit, stress is proportional to the strain produced in a body. So stress is proportional to strain, or stress by strain is equal to proportionality constant E. This proportionality constant E is known as modulus of elasticity. We shall know what is meant by elastic fatigue. So the state of temporary loss of elastic nature of a body due to continuous strain is called elastic fatigue. If the material is given some rest, that is kept in unstrained state for some time, then it regains its original elastic nature. Hooke's law is the law of physics that states that the force F needed to extend or compress a spring by some distance x scales linearly with respect to the distance. That is, F is equal to some k proportional constant k into x. So here K is the measurement of its stiffness also. And X is small compared to the total possible deformation of the spring. The law is named after 17th century British physicist Robert Hooke. So it is known as Hooke's law. Hooke's equation holds to some extent in many other situations where an elastic body is deformed, such as wind blowing on a tall building and a musician plucking a string of a guitar. An elastic body or material for which this equation can be assumed is said to be linear, elastic, or Hookean. Hooke's law is only a first-order linear approximation to the real response of springs and other elastic bodies to applied forces. It must eventually fail once the forces exceed some limit, since no material can be compressed beyond a certain minimum size or stretched beyond a maximum size without some permanent deformation or change of state. Now, we know about the definition of modulus of elasticity. The ratio between the applied stress on the body and strain produced in a body is called modulus of elasticity. This modulus of elasticity is three types. Young's modulus, which is represented by Y, bulk modulus, represented by capital K, and rigidity modulus theta. So, Young's modulus is the ratio of longitudinal stress and longitudinal strain. Bulk modulus is the ratio of volume stress to volume strain. The reciprocal of bulk modulus is called compressibility. The rigidity modulus is theta is obtained by dividing the tangential stress with tangential strain or shearing strain. So Young's modulus is the ratio of longitudinal stress to longitudinal strain. Longitudinal stress in the case of a wire is given by applied when external force is applied on the wire, then restoring force F bar is developed inside the body, which is equal to mg, and area of cross section of the wire is pi r square. And longitudinal strain of the wire is equal to change in length by original length, which is equal to dl by L. So longitudinal stress is equal to F by A, longitudinal strain is equal to dl by L. So by dividing longitudinal stress F by A with dl by L, we get mg by pi r square into L by dl, which gives the Young's modulus. So by substituting the values of increase in length dl and original length of the wire L and cross section area of pi r square value and restoring force mg, then we obtain the Young's modulus. So let us revise the basic of this elasticity part. Elasticity is the property of a body by which the body regains its original size and shape when the external force is removed. A body which regains its original size and shape when the deformation force is removed is called elasticity. Example, quartz bodies, steel, rubber. Stress. The restoring force per unit area developed inside the body is called stress. So stress equal to restoring force by area of cross section of the body. SI unit is Newton per meter square. Or in SI system, it is measured in terms of pascals. Dimensional formula of stress is m L to the power minus 1 T to the power minus 2. Now let us again revise the definition of strain. The change produced per unit dimension of the body is called strain. It has no units and dimensions. Stress is three types: longitudinal stress or tensile stress, that equal to F by A, and bulk stress or volume stress, F by A, shearing stress or tangential stress. Strain is also three types: longitudinal strain or linear strain, that is change in length by original length. Next, volume strain or bulk strain, that is change in volume by original volume. Third one, shearing strain or tangential strain, which is measured in terms of the angle. Hooke's law states that stress is proportional to strain within the elastic limit. Therefore, according to Hooke's law, stress is proportional to strain, or stress by strain equal to proportionality constant E. This proportionality constant E is known as modulus of elasticity. The ratio between the applied stress on the body and strain produced in a body is called modulus of elasticity E. Modulus of elasticity is three types: Young's modulus, bulk modulus, and rigidity modulus. Young modulus Y is obtained by dividing longitudinal stress with longitudinal strain. So F by A by dl by L, that is F by A into L by dl, or mg by pi r square into L by dl. Next, bulk modulus K is obtained by dividing volume stress with volume strain, and rigidity modulus theta is obtained by dividing tangential stress with shearing strain, or F by A by theta, that equal to F by A into theta. So these chapter, according to our syllabus, it is completed. If you have any doubt, please contact me. In the next class, we shall discuss about surface tension of the body. Thank you.